Calculating a line of best fit is mathematically trivial. Anyone can draw a plane through a cloud of data and find a structural fit. But how do we prove that line isn't simply modeling random noise? This 3D scatter plot shows a fitted regression plane. To evaluate it, we isolate a single data point. We can draw a strict boundary between the variance the model explains and the remaining error. That single point represents the atomic unit of model evaluation. To evaluate a model properly, we are going to deconstruct the mathematics behind it. First, by partitioning variance, then by deriving the covariance matrix for our estimators, and finally by untangling overlapping variables using partial correlations. Rigor in modern statistics depends on the systematic measurement and documentation of our own uncertainty. This diagram shows the fundamental mathematical identity of regression. A single point's distance from the mean splits perfectly into what the model explains and the remaining error. Squaring both sides of this equation and summing over all points yields the core formula. Total sum of squares equals error sum of squares plus regression sum of squares. For exam takers, note a crucial mathematical detail here. The cross term in this expansion sums strictly to 0. That is why the variance partitions perfectly, leaving no unaccounted fragments. This ANOVA table organizes these sums of squares. Each row carries specific degrees of freedom, n-1 for total, k for regression, and n-k-1 for error. Using this table, we calculate the residual standard error, or RSE, as the square root of the mean squared error. Notice the critical division here. We divide the error sum of squares by n-k-1 rather than n, adjusting for the parameters we've estimated. This mathematical partitioning proves exactly how much chaos the model has successfully organized. It establishes an absolute baseline for its overall utility. This pie chart represents the coefficient of determination, or R². We calculate it by dividing the regression sum of squares by the total sum of squares. This gives us the raw percentage of total variance our model successfully accounts for. Relying strictly on R², however, introduces a mathematical trap. Notice how this bar chart for R² ticks upward. Adding absolutely any variable to a model, no matter how irrelevant, mathematically forces R² to increase or remain flat. It creates a false sense of accuracy. Because of this automatic inflation, R² is merely a descriptive starting point. It cannot serve as an objective, standalone critical value for model validation. To find mathematical truth, we must shift our focus from the overall model's fit to the individual coefficients, specifically the B vector. B is strictly an unbiased estimator. To trust it, we must quantify its specific variance. This equation governs those parameters. The variance of B equals sigma squared multiplied by the inverse of x prime x. The theoretical unknown overall variance, sigma squared, is replaced by our calculated estimator, s², derived earlier. Looking at the inverse structural data matrix, the diagonal elements map directly to the variances of individual components, like beta 0 and beta 1. The standard error of a specific parameter is found by taking the square root of its specific diagonal element multiplied by s². This matrix algebra connects directly to standard hypothesis testing. Dividing the coefficient by this newly derived standard error yields the parameter's t-statistic. The covariance matrix acts as the ultimate mathematical lie detector for a coefficient, proving whether a variable is truly significant or just a structural artifact. Consider a practical scenario. Evaluating a regression model that predicts refrigerator prices based on size, features, and energy cost. This 2D scatter plot shows a counterintuitive diagnostic result. According to the output, higher energy costs correlate with a higher retail price.
Why would a consumer pay a premium for an appliance that is less efficient and costs more to run? The answer lies in a hidden confounder. Larger refrigerators inherently have more premium features, driving up the price, and their sheer volume naturally consumes more energy. Looking at variables in isolation creates a dangerous illusion. Omitted variable bias can completely invert the mathematical truth of a coefficient. To isolate true effects, we rely on the partial correlation coefficient and the added variable plot. This text outlines the mathematical mechanism. Step 1. Regress y, the price, on all other explanatory variables except energy cost, and isolate the residuals. Step 2. Regress xj, the energy cost, on those exact same explanatory variables and isolate its residuals. Step 3. By plotting these two sets of isolated residuals against each other, we strip away the overlapping effects of size and features. As this animation shows, the distorted positive slope morphs into a negative slope. We reveal the true, isolated negative correlation between energy efficiency and price. Rigorous modeling requires a unified framework. We start at the macro level, checking the entire system's validity using ANOVA and variance partitioning. Next, we move to the micro level, evaluating individual parameters using the inverse covariance matrix and t-statistics. Synthesizing these three levels of analysis, macro, micro, and partial, is how we extract precise, statistically sound insights from the noise of a raw dataset.
I seen folks rob banks with less hesitation than you got for hitting subscribe.